Welcome back to the third lecture. It's nice to see many of you back from the third lecture by Boaz Klartag from the Weizmann. Boaz,
Thank you, Michelle. Thank you very much. And thank you guys for showing up for the third lecture in this lecture series. So I suspect that maybe some of you came because of this pompous title, the unreasonable effectiveness of the convex assumption in high dimension. So my plan is to describe some, it will not be a philosophical talk, it will be a mathematics talk. I'll describe some examples and some situations where distribution with convexity properties behave as nicely as, roughly, as nicely as Gaussian random variables, pretty much in high dimensions. Along the years, there have been some conjectures, and some people express various opinions in writings about these conjectures, whether it's true or not. And I think now the verdict is that convexity assumptions are pretty strong in high dimensions. So if you know the distribution has convexity properties, it is a very good sign that to behave regularly. Okay, so that's the philosophy. This lecture is based on joint works with Pierre Bizol from the Weizmann Institute and Joseph Leheg from the University of Poitiers in France. Okay, and let me begin with something historical. The Poincare inequality, which is, let's say, together with the Minkowski inequality from the roughly the same period, is one of the, let's say, founding principles in this business. So actually, I know where Poincare published his work. So these are two papers from these years. The 1890 paper is from the American Journal of Mathematics in very good French. And the 1894 paper is in a Palermo publication. And the title of this paper is something like Partial Differential Equations of Mathematical Physics. And as part of this paper, Poincare proves the following theorem, which is now called the Poincare inequality. So let's suppose that we have a convex set in R3, okay? And the convex set is, let's assume it's open, not a big deal. And let's suppose that we have a function, a scalar function on this convex set K, zero and smooth, whose average is 0, okay? Then the Poincare inequality tells us that the L2 norm of this function is bounded by some parameter, Cp of K, some parameter of the domain K, times the square norm of the, times the square of the norm of the gradient of f, okay? In other words, if you know that the gradient of f is small, this means that the function does not fluctuate too much locally. You know, the gradient is small, so it's kind of constant. Then, thanks to the Poincare inequality, you get global information. The function, the variance of the function is bounded. And since we assume the integral is 0, you just say that the L2 norm is bounded. In general, it's the variance of the function which is bounded. Okay, and what Poincare proved? He proved that this so-called Poincare constant, this number here, is at most the square of the diameter of K. Right? And this makes sense because the unit, this is like 1/meter squared, so you need to multiply by this to get a dimensionless quantity. And yeah, he got this coefficient here, it's non-optimal. In 2 dimensions, he got a better constant, 7/24, smaller numbers than this one. A decade after the Poincare inequality appeared, the Wirtinger's inequality on periodic function in 1 dimension, which has sharp constant, but it's not any convex set, but just on the circle. And as I already said a few times without noticing, this Cp of K is called the Poincare constant of K, or more precisely I would say the Poincare constant of the uniform measure on K. Somehow we'll associate the Poincare to a probability measure. If you replace the Lebesgue measure here by some measure mu, they put Cp of mu, okay? Maybe I should write it down because maybe people would not remember this later. So definition of Poincare constant is it's the best constant in this inequality, that the variance of a function is at most the Poincare constant times the integral of grad f square with respect to this measure, and that's the minimal, the best. I mean, the best you can put there, the best, the minimal numbers that you put. That's the Poincare constant. Okay, now it's also, by the way, 1/the spectral gap of the normal Laplacian. I'll say what this means. If you don't know, some of you probably know, but if you don't know what's the normal Laplacian and the spectral gap, then I'll say a few words in the next slide. Okay, how did Poincaré prove this inequality? So yeah, you need to use convexity in one way or another. So the idea is that let us normalize K to have volume 1. That's nothing. Then the variance of a function f is half times the double integral which appears here. So it's half times f of x minus f of y squared, where x and y range over k. That's a simple thing. So what we need to do is to bound the difference between two random points, independent points in this domain k. So Poincaré looked at this f of x minus f of y, and what he did is just connect x to y by a segment, right? This is a convex set, so you can connect x to y by a segment, and then you estimate f of x minus f of y by the integral of the directional derivative of f along this segment. That's what you do. You replace these things, say smaller than the integral of directional derivative, and then all you do is just change of variables in Cauchy-Schwarz, and you're done. That's pretty much the proof of Poincaré. So, yes, please.
In the case where you have a measure, what does convex mean?
It will be log concave. Okay, it will be log concave. So I mean, just answer you. So log concave mu would mean that it has measure density. So it's density e to the minus h, where h is convex. Okay, so I said that you're right. So this lecture is relatively independent of the second lecture. In the second lecture, I defined it, but yeah, this would be the condition, log concavity. In particular, h could attain the value plus infinity, in which case you allow uniform measure on a convex set. So let's say in these formulations, then h, let's say convex, and you allow the value plus infinity, or you say that it's supporting. So if you put plus infinity, this vanishes, and or if you don't want this value, you say that h is convex and mu is supported in some domain k. So that's another possibility where k is convex. So h convex and k in Rn is convex, and then you don't need to say that, you don't need to allow this value. If you don't like it, then you just say that it's a scalar function. Okay, what was Poincaré's motivation for this inequality? Part of his motivation was related to the heat equation in R3, okay? So let's suppose that our domain K in R3 is an insulating boundary. Okay, so this means that heat does not enter this body and does not escape this body. Okay, and let's write ut of x for the temperature at the point x at time t. Okay, and this function, this temperature function, evolves according to the heat equation and according to the Fourier law. What is the Fourier law? The Fourier law tells you that the heat flux is proportional to temperature gradient. So it means that if you have little surface and you see how much heat would cross this surface in a fixed period of time, in a short period of time, the amount of heat that cross a fixed surface is proportional to the directional derivative, to the temperature gradient across this surface. So this is the Fourier law. And this means that since the boundary is insulating, so heat cannot escape, you get this boundary condition. The normal derivative at the boundary is 0 because we say that heat does not cross the boundary. Okay, so this is this boundary condition, and Fourier law also gives you the heat equation itself. If you look at the small box, you see what goes, you would get also this equation. So this is the heat equation. And now, if you have initial temperature distribution U0, okay, and let me suppose that, I don't know, at the average temperature times 0 is 1 degrees Fahrenheit, Celsius, Kelvin, something. Yeah, 1 is 1 equals 1. Okay, okay. Okay. Then what would happen to the distribution? So suppose that U0 has average temperature 1. Okay, and it's well, let's say that U0 is like this function. So it's a bit small. It's blue means cold, red means hot. So it's a bit small in this value region, it's a bit hot in these regions, okay? But the average is 1 of this function. Now, what would happen to the distribution with time? So since it cannot escape and cannot enter this domain K, then you'd expect the heat distribution to become more and more uniform as time passes. So you'd expect the function ut to converge to the constant function 1 as time goes to infinity. And this is indeed true if the set is connected and you don't have any nasty counterexample. And the importance of the Poincaré constant is that it governs the rate of the convergence to the equilibrium, to this constant function 1. So if I look at ut minus 1, then in L2 it decays exponentially with t, and the relaxation time is the Poincare constant. So if you wait Cp of k seconds, you get factor 1 over e decay in the L2 norm, and that's the importance of Poincare constant. And why is that true? That's because of the spectral composition of the Neumann Laplacian. So the Poincare constant that you see here is like the Rayleigh quotient. You can connect it to a Rayleigh quotient. You integrate by parts, you write this as, you integrate by parts, you write this as Laplacian of f times f in some way. Let me call it L. It's not exactly. You integrate by part, you get this thing. And then when you took the infimum of this thing, it's some kind of a Rayleigh quotient. And what you get is that there is this Neumann Laplacian is no spectrum. It has a constant eigenfunction with 0 eigenvalue, and the next eigenvalue is 1 over Cp of k. So you can get this this decay here. Okay, so this is the Poincare inequality. It was generalized in the 20th century to discrete set everywhere. You have the Poincare inequality, right? You have the in graph theory you have the Laplacian of the adjacency matrix, things like that. Yeah. Okay. So the Poincare inequality has lots of influence along the years. Okay. And why did Poincare look at convex sets? What is the reason? I don't know. It is not right about anything, but I can guess. So you can say maybe. So okay, it's pretty clear. This is true that the Poincare constant measures the connectivity or conductance of your domain. Okay. So if it is small, it means that the set is very much connected. If it's too large, then the set is almost disconnected. And you could say that convexity is a very strong form of connectedness. When you say that a domain is connected, you mean that if you have 2 points, x and y, there is some curve in the domain from x to y. But if you say the set is convex, you don't say some curve, you say segment. You have a very specific segment connecting them. And indeed, it's very easy to have counterexample without convexity assumption. So if you have, let's look at Poincare inequality. Suppose that this dumbbell, you say in English? Yeah, it's dumbbell. Suppose this dumbbell has a diameter 1, okay? Still, if it has this bottleneck, if it's not convex, it will take lots of time for the heat to cross this bottleneck and to fill the other side. So without convexity assumption, you cannot have a clean bound for the Poincare constant in terms of the diameter. It's kind of helps you have a balanced set. Good. The Poincare inequality was proven not only in dimension 2 and 3, but also in all dimensions, okay? This was stated by Payne Weinberg in 1960, and the proof was, let's say, proved and made more rigorous by Gromov and Millman, and by Kanan, Lovash, and Simonovich in the 80s and 90s. And we have the following theorem with the sharp constant, so let me read it out loud. Let K in Rn be a convex set, and let mu be any low concave measure supported on K. So it means that its density is e to the minus h, where this function h on this domain K is a convex function. For example, if you take the constant function, you get the uniform measure on K, but you can get other things. You can get the Gaussian measure also, if you want, or other things. These are low concave measures. And then for any function f integral f0, the integral of the square of the L2 norm of f is bounded by this quantity times the integral of the gradient square of f. And that thing here, the Poincare constant, is at most the square of the diameter over pi square. Okay? And you see that there is no dimension dependence here. It's just diameter over pi square. The proof by Poincare would not give you such a good constant. It would give you some things that goes exponentially with a dimension. But fortunately, there are techniques like something called convex localization, some hyperplane bisection method that will give you this constant pi square. This pi square is actually best possible in any dimension. In dimension 1, it is optimal because I can take interval of length pi, and I can look at the sine function. So sine function means 0 on this interval, yes? And the integral of sine square and cosine square are the same. It's like half, right? Sine square. So yeah. So this and diameter. So this is that example in dimension 1. And in dimension n, you pretty much reproduce this example. How would you reproduce in dimension n? You take a cylinder, take this segment, unit segment. Let's take Cartesian product with a very, very tiny ball in n-1 dimensions. which would not influence anything. And for that very thin cylinder, the Poincare constant would be almost pi square. I mean, it's almost the same. So the cases where this inequality is tight are almost one-dimensional examples, okay? So this is about the Payne-Weinberger inequality, the Poincare. However, if you look on domains or distributions that are not one-dimensional, that are really n-dimensional, like things like the cube, the ball, simplex, I don't know, Gaussian measures, this is pretty much, I don't want to say useless, but it's, it's off by a huge factor. So for the cube, the diameter is square root of n, the Poincare constant is roughly 1. It's not good. The ball the diameter is 1. The Poincare constant is 1 over n. It's the same. So it's usually used off by a big factor. And if you think about applications that we have in mind, for example, people that chemistry know about the thin shell theorem, then you just get nothing if you apply the diameter bound for the Poincare in that context. So it's in high dimension, you don't want to use diameter at all as a parameter for the Poincare inequality. And in this lecture, we'll discuss another parameter, another geometric parameter of the domain K, which makes more sense for estimating the Poincare constant. Let me just tell you that in addition to Poincare constant, there are other ways to measure conductance or connectivity. For example, there is the isoperimetric constant of a convex open set. So what is this isoperimetric constant? It is the following thing. So I look at all possible ways to partition my domain into two parts, let's say of equal mass, or let's say of equal mass. And among all possible ways to partition my domain into two parts, I look at the partition that minimizes the n-1 dimensional measure of the interface, okay? So it's the infimum, more precisely, it's the infimum of this is n-1 dimensional measure. Let's suppose that this is a smooth boundary. And I only take, the set K is open, I really emphasize it, so we understand that you don't take this part of the boundary, you take the boundary of A inside K. So only this blue part is taken, you don't take this thing because it's not in the open set. So you take just the interface which is inside your domain, and you divide by the minimum of the measure of A and the measure of the complement. Okay, this is called the Chigger constant, or the isoperimetric constant of your domain. Okay, it is known that under mild assumptions, it's enough to look on balance partition, half and half. This was proven by Sternberg and Zubrin in the end of the 20th century. Okay, and another nice thing, so it is known from the works of Chigger in the general case and Boozer and Ledoux in the convex case, that the Poincare constant deviates from the Chigger constant to appropriate power -2, by some universal constant factor. So this is, by the way, tight. This is the Chigger inequality, which does not require convexity. This, I think, better constants are known. I didn't write them down by Mondino and others. But okay, 9 is not the optimal constant, and the optimal is known, and I forgot what it is. Okay, but up to universal constant, the Poincare constant measure connectivity, isoperimetric constant measure connectivity, and they are kind of the same. If you measure like station time it wouldn't matter that much. And also there are other ways to measure connectivity. You can run some Markov chain on your domain and look at the mixing time, and usually things would really be close to the Poincare or to the isoperimetric constant, maybe up to log here and there. These Markov chains were used by Dare, Fries, and Kanan in the end of the 80s and later by other people for sampling and for estimating volumes of convex bodies in high dimensions. And by the way, even if you just have this proof by Poincare, and you would think that the Poincare constant grows exponentially with dimension, it would be very bad news for these algorithms, because you could think that the algorithms would need exponential in the dimension amount of time to mix, which renders them useless, because the rules of the game in complexity theory is that exponential is bad, polynomial is good. But fortunately, we know that the Poincare constant does not grow that fast, so the Markov chain does mix in a reasonable time. Okay.
Can I ask, so is
should have a Riemannian manifold, then you should require a positive curvature, and then there will be also a point where constant. Yes, yes. So there is the Lishnarovitz inequality. Yes. So suppose that you have a Riemannian manifold. Okay, let me make it geometrically convex. And you know that the Ricci curvature is everywhere at least some number, at least some t times g. Then the Poincare constant, you understand, I guess, what's the Poincare constant of this? It moves to 1 over t. T is positive. Okay, this is Lishnarovitz in the 50s. Lishnarovitz 50s. Yeah. And we will see, so the Ricci is analog. So if my measure is log concave, I said that it has a density e to the minus h, then the Hessian of h is pretty much analogous to the Ricci of the manifold. It kind of plays similar roles.
Is there pi square constant appear there?
Yeah, same. Yeah, this one. Yeah, same. Okay. If Ricci is non-negative, so non-negative is log concave, right? Non-negative means that it's so exactly true with the same constant. So if you have a Riemannian manifold where the Ricci is just non-negative, Poincare is pi square over diameter square. Exactly. So no difference, and actually same proof even. Okay. More questions? Yes. Okay. So let me say. So these things are pretty much in. Just said things about high dimensions, but those mostly result in a fixed dimension, which are maybe easier to digest for people. But now I want to increase the dimension and tell you a bit about this study of uniform measures on convex domains in high dimensions. So the questions that we ask are not trivial only when dimension tends to infinity. And one nice feature of this field is that we kind of use, I would say, slightly more techniques than in some other fields, like there's 5 techniques. So there is this convex localization, this hyperplane Nadel's decompositions, optimal transport, even L2 or L1 actually is also pretty useful. All this Bochner formula from Riemannian geometry is especially useful. We use the heat flow, we use geometric measure theory, like Sternberg-Zumwalt result is geometric measure theory. You analyze the optimizer of the isoprimic problem. And there is this Eldon's stochastic localization technique, which is much more refined estimates for the heat flow. So this is this field. And our theme, what I try to sell, is that convex in high dimensions is a source of regularity, which will compensate for lack of structural symmetry. So in some sense, if you have distribution in R which is log concave, uniform on some polytope, then it's kind of a Gaussian of the same mean and covariance. So you really need to know what the mean and covariance, and then sometimes it's like a Gaussian, not always. Okay, these are big words, and let me explain a very simple example of a convex set to justify these big words. And that simple example would be the unit ball. It's the simplest convex body you could think of. It's better than the simplex, I would say. Yeah, okay. It's the most symmetric convex body you can think of. And the Euclidean unit ball has most of its mass close to the sphere, so we can either think on the ball on the sphere, doesn't really matter. The sphere is slightly nicer because it's homogeneous space, so let's discuss that. So the claim is that we have this following spherical concentration of measure, which is the following effect. So first of all, most of the mass, so the sphere is, let's say, normalized to, let's look at uniform probability measure on the sphere. Most of its mass is close to a narrow strip near the equator on the sphere. That's one property, which is why we sometimes depict, this is what I learned from Vitaly Milman, my PhD advisor, that you should draw the sphere like that in higher dimensions. I learned many other things as well. But what you don't see in this picture is that it's true for many equators, not just one equator. For all equators, the mass is close to the equator, which is nice. And moreover, if you have any, say, continuous function f, where 0 is its median, then most of the mass is close to this kind of nonlinear equator. This level says f equals 0. So there are, this is spherical center of measure. Why is that true? How to prove it? The first point is that if I take uniform distribution of the sphere x, then I can write down, by Pythagoras' theorem, I can write down the density of x1. And what is density of square root of n times x1? The density to be supported on minus root of n to root of n, and it will be just 1 minus t squared over n to the n minus 3 over 2. proportional to this thing. And if you look at this expression here, you kind of see it's kind of Gaussian. This was known in, if you just say that n goes to infinity, you get n minus t squared over 2, and that would tend to 1 over square root of 2 pi. So you know that you have square root of nx1 is roughly a standard Gaussian, okay? So it means that square root of nx1 attains value, I don't know, between minus 3 and 3 typically. So x1 attains only values between minus 3 over square root of n to plus 3 over square root of n, which is very, very close to the equator. This is the first, second point. For the third point, how do you do nonlinear equators? You just use the isoperimetric inequality in high dimensions. So the isoperimetric inequality in high dimensions, proven by Paul Aviv, in any dimension, says that if you divide the sphere into two parts of equal mass, okay, and you want to minimize the epsilon neighborhood of this surface that divides it in two parts of equal mass, then the minimal possible epsilon measure of mass would be for the hemisphere. So if you take an equator, it minimizes the epsilon neighborhood of the set among all possible sets that divide the sphere into two parts of equal mass. So this would be, so the behavior is only better or only worse, I mean stronger for nonlinear sets than for linear sets. So that's why you know that for any continuous function whose level set at 0 is a median, where 0 is a median, you have strong concentration near this level set. One corollary of this spherical concentration of measure is Paul Aviv's lemma, which says that if you have a one-Lipschitz function on the high-dimensional sphere, and you write E for the average of this function with respect to the probability measure on the sphere, the uniform one, then the function f rarely deviates from its mean by much. So if you look at the measure of the set of points where R deviates from its mean by more than epsilon, this is very small. It's only e to the minus epsilon squared times n. So if epsilon is fixed, like 0.1, this decays exponentially in n. So if you sample like 5, 10 points and evaluate your Lipschitz function, one Lipschitz function that is 5, 10 points, you'd get the same number all the time, roughly, with small error, which means that Lipschitz function on this high-dimensional sphere behave in some ways as kind of effectively constant. That's an important technical step in several proofs. In particular, this lemma is the main ingredient in the proof that if you have a thin shell bound from yesterday, then you get approximately Gaussian marginals that I mentioned yesterday. Okay. Now, this was the case of the ball or the sphere, this concentration measure for the sphere. It's good and useful. And our task is to generalize. So we're not happy with having just concentration measure for the sphere. You can say that the sphere is already almost Gaussian. It's not, but we want to understand the convexity assumption in high dimensions. Okay. So we want to ask whether there is a similar concentration phenomena for general convex bodies in high dimensions. And the answer is yeah, pretty much yes. Okay, so there are strong expansion properties. So if you want convex sets in high dimensions are good expanders, and the isoperimetric inequality, more or less like the case of the sphere, is saturated by half spaces up to a constant, up to small error. So I mean, if you want to partition a convex set into two parts to minimize the interface, take a slice like with a hyperplane, and it would be not that far from the optimal one, like you get for the sphere. But there are some changes. It's not exactly the same. Say for people who work in probability, the main difference is that the tail of Lipschitz functions was here, it was sub-Gaussian, you go this epsilon square, and the tail for convex is just sub-exponential. So you get like just like root of this thing, like epsilon root of n rather than epsilon squared times n. So this has some effects here and there, but other than that, it's kind of pretty good. So if, what? Okay. Yeah, so I can repeat the question. The question was, what is small set expansion? Okay, so the Chigger inequality, can I take this down? So the Chigger inequality tells you that if you have that if you have a set whose measure is, say, 1/2, okay, in your space, let's say, then you know that the epsilon enlargement, say, then for small epsilon, what you get would be roughly at least, let's say, some constant, depending on you, times epsilon, times the measure of A. So this is what you get from the Chigrin inequality. And small set expansion means that it gets better if the set mu is small. So you get something better than that. Small set expansion means that you get a log factor. So you get the same, but you get mu epsilon times mu of A times, let's say, square root of log of 1 over the measure of A. So so this is this was H mu, I think, in my notation. Okay, so the idea is that the isoperimetric, if you know the isoperimetric constant of the measure, you know that for any set, its boundary is at least its measure, right? We divided. You remember the definition of so we divided by A and so this was the infimum of the boundary divided by A. Okay, so let's ignore that. Suppose A is smaller than 1/2. Let's say that A is smaller. So this is the minimum. So you know that the ratio of the enlargement to A is at least this number. But small set expansion means you get something better automatically. This is true in the Gaussian order in the sphere. Not only, so this is how you find this opportunity, you get by chance something better. You get a log factor here, which corresponds to having some Gaussian tail in the value distribution of Leibniz functions. So this is small set expansion.
Is it because the sphere has strictly positive curvature as opposed to non-negative?
Yes. Yeah. This is the reason. More questions? So let me tell you about a conjecture called the KLS conjecture after Kananovich and Simonovich, which states what I said, that any convex set has good properties like the sphere. This KLS conjecture has 3 equivalent formulations, okay? Concentration, Poincare, and isoperimetry. So we conjecture that if we have say, a convex set in Rn, we consider the uniform probability measure on the sphere, and we assume that we have 0 mean identity covariance. So we normalize our set K to have a mean 0 identity covariance. Then we conjecture first that, first formulation, if you have any one Lipschitz function whose average is 0, it has uniformly sub-exponential tail, okay? Okay, so this, just for you to know, the unit sphere has small variance. You need to take 0 variance. This corresponds to what we have for the sphere, up to replacing quadratic by linear exponent. The second formulation under this normalization is that, so for the Gaussian, you get t squared. That's the only difference for the Gaussian. The second formulation is Poincare inequality, so there is some universal constant C. All these C's are universal constant, just numbers. For any smooth function f, you have a Poincare inequality with universal constant. Okay, and the third equivalent formulation is this perimetry, that there is some universal constant such that for any set with a smooth boundary, the volume of its boundary is this constant times A and the complement. Okay, these are this is the KLS conjecture. It is still open, and the best known result is that you can, it's up to log factors in the dimension. So if you put here like 1 over root log, and here log, and here 1 over root log, then it's okay. This is the best known result, but that's still a conjecture at this point. Yes, please.
The extremal A in the third, would it want conjecture to be a hyperplane or not necessarily?
It's not conjecture. Okay, so it is conjecture. Let me do some quantifier change. So conjecture is that if you take a hyperplane, then up to factor 10, it's as good as the optimal. So it does not mean that the optimal is, it's not true. I mean, if you take a planar domain, I don't know, then you usually get an arc of a circle. That's the optimal way to partition it. Okay, the optimal is usually an arc of a circle and not
But for hyperplanes, it's within the
But
constant.
if you do this, you just lose factor 5.
Okay.
That's the conjecture. Okay, more questions? Okay, so this is the conjecture. But let me now, okay, but this was under the assumption that the measure here had 0 mean and identity covariance. What would you get without this normally? Well, and it was not, okay, these equivalences are completely non-trivial. This is due to Boozer, and Chigurh, and Gromov and Edu, and Vitali and Emmanuel Millman. Okay. And also, the bound that I said is not just my work. It's many people did. And okay, so it was built on the work with Lehek and Ronen Eldani's PhD, and Lin Vempala, and also a bit Chen. Actually, yeah, okay. Good. Now, what about, what if you forget about the normalization? So I don't want to have a mean zero identity. What should I say? So the conjecture is that if you just have, without any normalization, so local distribution, we conjecture, as we said, that isoperimetry is saturated by hyperplane bisections, and the Poincare inequality, which is not written anymore, but here it will show up. Yeah. So we conjecture that this is saturated by linear functions, pretty much. Okay, that's the Poincare inequality, currently known up to log factors. Okay. And this means that if you want to estimate the Poincare constant, it's enough to test linear functions. Now, if you have the function scalar product x with theta, where theta is unit vector, this right-hand side is just 1. Okay, so you just want to take the supremum of the variance of x times theta, and this is the operator norm of the covariance matrix of x. Okay, so just some linear algebra. This thing is what you get if you only apply linear functionals in the Poincare inequality, and that's for all non-linear functionals also. And the conjecture is that kind of linear, okay? Okay. So we think that Poincare, one more time, we think the Poincare constant should be roughly the operator norm of the covariance matrix of x. Okay, and there is an analogous property for sections. Hyperplane bisections are roughly the best solution for the isometric problem. Can you guess? Can you guess? Yeah. Yeah. It's like variance of f of x. Actually, it looks a bit even. Should I? Okay. Variance of f of x is smaller than Cp of x. Expectation of grad f square of x. Okay, that's the. Yeah. Yeah. Okay. Now, so there is some hierarchy of conjectures. Yesterday we discussed Sinchen and slicing. There was solved, and KLS is okay. It's not solved, but it's in good shape. You know, it up to log factor. So we kind of see that somehow, a bit unexpectedly. I mean, people would okay. So it's not clear, but it seems that convex very high dimensions are pretty regular. Okay. So why? Why is that? Why do you have this effect that we get this strong concentration for just under convexity assumption? And one possible kind of philosophical explanation is that maybe they're all like the Euclidean ball. Maybe they're all pretty close to the Euclidean ball. Okay? So let's try to begin discussing distances between convex sets. Okay? And the familiar distance between convex bodies, between norms, between Banach spaces, is the Banach-Mazur distance. Let me tell you what this Banach-Mazur distance is. So you want, I mean, the distance should be such that all ellipsoids are of distance 1. I mean, all distances should be close to each other. You want to measure distance up to linear transformations, because this is the diversity you have for Gaussians. Gaussians are all linear images of one of each other, right? So you want to mod out by linear transformations and then measure the distance, okay? And that's the Banach-Mazur distance. So the measurement distance between two convex bodies, how do you define it? You take your favorite linear transformation and favorite translations of these two convex bodies, and then you require that after this linear transformation, one body would contain the other, but if you scale the other one by factor r, it will contain the first body. Okay, so this is the Banach-Mazur distance. Like in this shape, you see k scaled by factor, k is inside T of L, and after you scale by a factor of r, it contains T of L. Okay, this is the Banach-Mazur distance. And Fritz-John proved in 1948 that for any convex body in the world, if you look at its maximal volume ellipsoid, you get this linear map T from the Euclidean ball, and the Banach-Mazur distance from k to any ball is at most n. This was proven by Fritz-John, and there is equality for simplices. Okay. Now, the question that arises is if you have, okay, so all of them have distance n from a Euclidean ball, how close are they to one another? We recently improved. So Rudelson had a result, a very strong result, saying that it's n to the 4 over 3. This is a multiplicative distance. So if you have k1 to bn and bn to k2, you get factor n squared. And we were able to improve this, building upon lots of work by Chavez inequality and Millman-Pizier and Dan Leck and Emmanuel. We were able to get n up to log factors, so which is tight. Another thing that we know about this Banach-Mazur distance is that our boundary here is realized. So we need to choose the linear transformation, and what we do is we put both bodies, we normalize the covariance, they are centered, and we know the covariance will be identity, and we apply random rotation. So if we just do that, it's not good enough, because you can have, I don't know, for example, a cube and a cross polytope. In order for them, you can have situations where we need to scale by factor of n in both directions, get n squared if you take both isotropic position. But then you apply a random rotation, and then it's just root of n, and you get this estimate. So this is how you would bound the Banach-Mazur distance between two convex bodies. And there is one difference. So let me just say that there is if you kind of try to understand convex bodies up to this Banach-Mazur distance, how closer to each other, in the centrally symmetric case, there is an approximate center to this Banach-Mazur compactum. In the centrally symmetric case, indeed, there are convex bodies whose distance is roughly n. So this is tight. But any convex body centrally symmetric is distance square root of n to the Euclidean ball. So the Euclidean ball is if you want to move from one convex body to the other and you go through the Euclidean ball, you will get a factor n, which is as good as it gets. But somehow in the general case, of general convex bodies, we don't know if there is an approximate center. So the body is not an approximate center for sure. Yeah, it's kind of interesting if there is one or there is no one. Okay, so this is about the Banach-Mazur distance. But let me now tell you, and in that Banach-Mazur distance, you get like convex bodies are far from each other. They are like distance n, which is a big number in high dimensions.
Is there an analog log concave distribution?
Yeah, you can. How would you define it? If you want to scale it really larger than the other, yeah, there are some analogs like that. You need to, yeah. It's less clean, but there are. Yeah, definitely. Pretty much everything about convex bodies was generalized to log measure in the last 25 years. It was kind of there is such an industry of generalizing things. Yes. Okay, but my message right now is that the distance between two convex bodies can be n, can be a large number, right? They're not the same. K is not like Euclidean ball, n is a big number. But there's a different point of view, which is not to use the Banach-Mazur distance, which is kind of rigid, but use something more relaxed, which we call the partial containment distance. And that definition was inspired by a lecture of Apostolos Giannopoulos that we heard and by correspondence with Larry Guth. And that's the following definition. So the Banach-Mazur requirement was that one body, after we scale it, contains the full other body, right? We did not leave any, we were very strict about to contain 100% of the other body. But let's be more liberal and let's try to allow 99% containment. Okay, so we are okay if we only contain most of the other body. Okay, so we define the partial containment distance between two convex bodies K1 and K2 to be uniform over all R, such that if you take the right linear map and right translation, you get two convexes Q1 and Q2, such that Q2 contains 99% of Q1, and after we scale Q1 by factor R, it contains 99% of Q2. Okay, so you don't contain, but let's say that this part here is 99%. So you allow yourself some 1% error in this containment. And then it turns out that this n factor becomes only log n, or polylog. So up to log to power 4 or 3.5 or some small exponent. We know that any convex bodies are relatively close to each other in sense of measure. Okay, so this
Does this relate to M ellipsoids, or they're different?
So maybe you can find some relation, but it's rather indirect. M ellipsoids are ellipsoids that represent k in volumetric computations, but up to an error of 2 to the n. So, right, exactly. It's not, and we do like 99%, so we do something way more accurate than ellipsoid. The Weizmann ellipsoid, let me tell you, it's a theory that was, so before it was way to circumvent slicing, to have something weaker than slicing and kind of still get result. This was the, and we are like after slicing, we are in a more accurate world. More questions?
The sharp ends don't mesh. But if you
Exactly, but they're nothing. The sharp ends are often as mass. Yes, please.
Yeah, so I mean, when you define two convex bodies, maybe the Banach-Masur is the natural thing to do. But if you do what Pavel asked, which is moving two measures, then you have a slew of distances between non-concave measures that you can think of. And so, let's say I want to look at the TV distance, or anything.
Also,
are there any such questions that make sense for just distances?
Yeah. I will show you. Okay, I will show you results for low concave. Yeah, there will be a nice theorem about low concave and Gaussian in 2 slides. Okay, maybe if you answer the questions, then yes, and otherwise you can complain. Okay. Let me give you more corollaries of this. Okay, read that in the meantime. Okay. There is the following corollary of this theorem. So basically, if you take your convex sets and you center them and you normalize the covariance to be the identity matrix, okay, this isotropic position, then both of them are close to each other in the sense that if you take one of them and scale by a log factor, it would contain the other, and of course also the other way around. These are symmetric conditions. So convex bodies we say in a isotropic position, but identity covariance and centered, you scale by a factor log, one contains the other almost 99%. So this is a nice corollary which says that they're kind of close to each other. And now these distances, the cleanest formulation in terms of convex sets, the low concave version is pretty messy and it's not as good as W2. It's not true in W2 or W1. However, if you want to have a nice formulation for low concave distributions, the nice thing is to look at some family of observables. And for us, it will be the norms as the observables. So we have the following theorem that is proven by combining our work with Eldani and Lehek from 2013. So what we proved is that if X is a centered low concave random vector in Rn, and I take a Gaussian with the same center and the same covariance, then if I look at any norm, okay, actually I can take even more, any convex functions that does not go too fast would be okay. But say any norm, this is applications, working norms. If I take any norm and I look at the expectation of the norm with respect to this low concave random vector, or with respect to the Gaussian, I'm off by log n. So that seems like a useful formulation. While you put some artificial distance with low concave measures, you can never use it. This is my impression. But that could be used. So that's what, if you have nice prime which is elegant and can be used, I'll be happy to hear. Okay, so this is our result with Pierre, building on Daniel Heck. Okay, now in the last 10 minutes, let me tell you a few words about how do we prove KLS and our work with Pierre and with Bizol up to log factors. Okay, so So one thing that we like a lot is uniformly low concave distributions. They are way nicer than just low concave distributions. So as Pavel remarked, if the radial curvature is strictly positive, it's better than if it's just negative by much. And the same holds in the low concave world. So if I have some, my notation, mu is low concave measure, its density is rho, and rho is e to the minus psi. So psi is a convex function. Now, if we were not, so the action of psi is non-negative, this is we know. Had we known, oh no, I should not press, okay, okay. Had we known that, that the action of psi is not just non-negative, but in fact strictly positive, at least t, then by this Bochner method that I told you about, those who were yesterday know, the Bochner method, you get that progression at most 1 over t. Okay, so we get a uniform bound of 1 over t for progression, which is very good. But our distribution is not uniformly low concave. It's, say, uniform on the simplex, uniform in some convex set. What would you do in such a case? And then there is a very important observation of Ronel Eldani in his PhD. I mean, it was known also in retrospect, you could say that there were precursors, but I learned it from him, which is that you can decompose an arbitrary low, if you have n low-K distribution, rho, you can decompose, you can disintegrate the measure into a mixture of distributions which are more low concave. The elements of these mixtures are T uniformly low concave. The Hessian is larger than T. You can do it for any factor T, you can find such a mixture. Okay, so let me tell you what is this mysterious decomposition. It's actually a very simple object. So there is a simple construction based on the Gaussian convolution, which I'll explain in the next slide.
Sorry, is this the same as like Hubbard-Stratonovich decompositions, or?
Stratonovich could be.
Okay.
I'm not sure. So it appeared in Theory of Nonlinear Filtering. I keep hearing earlier and earlier references for that. In the work of Follmer, you had things like that. But nobody uses so the idea to use low concavity is only Eldon. I think nobody used in the context of convexity these decompositions. Yeah, I will show, the construction is just a little take on the heat flow. It's nothing, I'm sure it appeared. Stratonovich makes sense. I would not, don't know about it, but yeah. Okay, so what is the construction? So what are the elements of the mixture? Okay, let me tell you what are the elements of the mixture. Each element of the mixture is just the original density rho times a Gaussian factor. The Gaussian factor, I like to write it this way. The quadratic form is always T times x over 2, plus some linear thing here. That's the quadratic, and this normalization constant. This is the Gaussians that we multiply our density rho by this one, and you see that the Hessian of this factor is exactly T. This Hessian is non-negative, so we get uniform low concavity. Okay, this is the idea. Now let me explain to you how this the composition works. Okay, and for that we need to use the total law of probability. Okay, so what is this integration into T Gaussian tilts? The claim is that
so there is some range of T and
each T, everything.
For a range of T, I don't know how this mixture is distributed in T, or doesn't matter.
Okay, so this equation is an almost algebraic construction, works for any T in a very simple way. But you need to any fixed T.
And for the measure that you start with low concave, don't have any parameter T.
No.
What do you lose when you decompose it? This is extra property.
Okay, so you have the Poincare constant for this. Each of the pieces of the mixture is good Poincare constant, but you need to relate to the original measure. So for example, suppose you decompose into delta measures. Delta measure is Poincare constant 0, the best possible Poincare constant in the world. But it's useless because you cannot relate the Poincare constant of the delta measure to the original Poincare constant that you started with. So this would not be useful. You want to have some balance between, you want the pieces of the mixture to be close to the original measure with T as large as possible. This is the game. So you cannot. Same Poincare constant for KLS. Okay. So there is a standard construction. Let me just tell you the formulation of the lemma. If you have, if X is a random vector with low mu, and Z is independent Gaussian in Rn, and if I write theta to be the sum of X plus Z, let's assume T equals 1 in this proof, T equals 1. So theta is X plus Z, then the conditional law of X given theta, what is it? So you have just, Rn times Rn, you have some product distribution, you slice it in diagonal, and that will be the conditional density of X given theta. Okay, and by the law of total probability, the original density of X rho is just the average over theta of the conditional measures. Okay. What is rho?
Mu is rho. What is mu?
This is not my problem. I said mu is local measure with density rho. See. I was careful because yesterday now I'm okay. Yeah. See, mu measure, rho is the density. Okay. Perfect. What? Okay. What's it? No, you cannot do that. What is it? No?
I like Greek letters, so let's do it.
You like what?
Let's do it. Let's keep going.
You like the Greek letters?
Yeah, let's go for it.
Okay, very good. Okay, so this is the composition, something completely almost trivial. Okay, and this is the same formula. The formula is you take rho times the Gaussian and normalize. This is the same formula. Okay, but now as I was asked by Sasha, okay, so I have these elements of the composition. Each element has a very good Poincare constant, and I want to relate the Poincare constant of the original measure to the Poincare constant of these elements of the composition, okay? So rho of theta for me is a random variable, rho of t is a random element of the mixture, okay? Theta is random, so this is a random element of the mixture. And there is some little computation that shows you that for t, which is not too large, for t, which is up to 1 over the Poincare constant of rho, you can show that the pieces of Poincare constant, which is roughly like the original measure. Okay, I will not explain this in detail. This you can read in a road service. It's not very difficult, just 1 or 2 pages. Okay, and then what will I do? I'm going to use not just the Lishner. So this fact is true in Riemannian geometry that you get 1 over t. But you know, Riemannian manifolds have their drawbacks. And what we were able to prove in RA, in the concave case, is that we have a recent, from 2023, improved Lishner-Horowitz inequality, where you get square root of 1 over t times the covariance, the operator of the covariance matrix. So if you want, it's geometric average of the KLS bound and the 1 over t that you get from Lishner-Horowitz. This has no analog, as far as I know, in Riemannian geometry, but only 3 years have passed. So maybe people would find something. This is super useful for us, and it was a source of great breakthrough. And then if you just plug in the estimate that we get with the improved Lishner-Horowitz, you can bound the Poincare constant of rho pretty much with itself times this quantity. And then what remains to be proven is that you want to find t as large as possible, for which the operator norm of AT is, say, bounded by 5. Okay? And this is where you need to, up to now, t was just any fixed number. But from now on, we had better let t vary from 0, etc., etc. And we replace square root of 2z by wt, which is the Brownian motion. And there are some computations from Eldan and from Lin Vempala 10 years ago, which shows that up to a certain time, depending on the Poincare constant, you get that, it's kind of, how to call it, bootstrap estimate. So up to this time, depending on Poincare constant, you know that AT does not grow, it starts at 0, the covariance, it stays 5. And then you get this equation, which kind of proves the KLS up to a log factor, okay? So I was planning to tell you how to prove this. It's not super difficult, but I will not show you that thing. What I want to explain to you is about a few words about this proof, okay? In the last 2 minutes, how do you prove that for any centered log concave random vector in Rn, these norms are very close to each other? First of all, the log n's are not artifact of the proof, they're really there. There are examples. If you take x, which is uniform in a cube, y, which is exponential, g, which is Gaussian, then if you take the norm to be the infinity norm, on the cube you would get 1. Gaussian, maximum of n Gaussian random variables is root log n, and for exponential you get log n. So there are really differences of square root of log n. It's not just a artifact of the proof. And the way we prove that thing is the following. So yesterday we discussed something about the thin-shell theorem, and we were able to represent x. So given a measure mu, we found some martingale that converges to this measure mu. And that martingale had the form, so it's integral of AT dBt. This has the law of the measure mu. But we understand that this process AT is relatively close to identity. So this means, in the low concave case, so this means that we can represent any low concave measure as a martingale that is roughly like the Gaussian martingale, at least for short times. Okay, and from this we can conclude. So we say that, I mean, if you have a lower bound for these martingales and for any convex function, it's bigger than the Gaussian. And let me just finish by using a result from the first lecture, right? Because wasn't it Chekhov who said that the lemma in the first lecture should be applied in the third lecture? So yeah, so if you have if you represent your martingale with quadratic variations bounded by R, then you can write it as a mixture of 2 standard Gaussians, and therefore for any convex function, any norm, you can bound the value here by the average of the values there. So this is roughly the idea of the proof of this result with the Bizol and Eldan and Leek also. Okay, so my time is up, so thank you very much for your attention.
Thank you, Boaz. Any questions?
So thank you for your talk. It was interesting to me that the bound you give for the Banach-Mazur distance between any two convex bodies is essentially what you get from the trivial bound, right? So just up to a log factor.
No, the time we're going to get n squared. No. So, okay.
Oh, the n squared. Okay.
Okay. If you take a convex set to a ball, this is a ball.
Sorry.
This is at most n. Okay.
So the n squared. Okay, sorry.
So you get n squared. If you have k1, k2, you get n squared.
Okay, so I guess my question is less valid now, but have there been attempts to see if you can construct convex bias K1?
This was like the state of the art for many years, the 4/3.
Yes. Can you construct, say, convex bias K1, K2 that are, say, random, that more or less show that your result is sharp?
Yeah, this was what, yeah.
Oh, this is Gluska. Okay.
Yeah. So what do you do? Let me tell you. You take the cross polytope and throw just n Gaussians in two such convex bodies of distance n.
Hi, thanks also for the talk. I was going to ask, when you start from a measure, log concave measure, and then introduce this, t and a theta, where theta is the tilt, if your initial row,
okay, yeah.
if the initial row is uniform measure on some, let's say, one symmetric convex body, do you need the theta still, or?
It's very unknown. Let me tell you, even in that. Okay, so for many years, KLS was solving the unconditional case up to some log factor.
Yeah.
But now the new result is better than what was known in the unconditional case, and we don't have any advantage for the symmetry because this process does not represent. So these new techniques pioneered by Ronald Eldan really washed away all of the previous methods, so it seems. And we don't know how to use this one symmetry or this unconditional symmetry.
Even in that case, I still need a random tilt.
I don't have a tiny improvement in that case of the. Yeah.
I see.
Even
okay.
It's a shame on us, but yeah, that's the situation.
Any other question?
So in the relaxation of the Banach-Mazur distance, if you allow 99%, are there examples that you actually get log n, or it can be all?
Thank you. These examples, for example, take the cube and the ball, you get root log. So just think. So the cube, random point on the sphere, the max of the coordinates is root log over something. So for the ball and the cube, you get root log. And for the cross polytope, so this is the ball, this is the cube, the ball, and the cross polytope. These are the relations that you have. So we have at least a log between the cube and the cross polytope. Thank you.
In the partial containment, if I have 1 minus some function of n, when do I expect to see a polynomial?
So very good. What is the dependence on 99% as a parameter? So it's logarithmic. Okay. For sure in the centrally symmetric case is logarithmic. This I'm 100% sure. I suspect also in the general case. But yeah, it's log. The distance would be, if this is epsilon, it would be just log of epsilon. Okay, because there is an exponential tail for norms of okay.
Thank you.
Okay, so
So there is a 1 over t. So you explain that when it's strictly positive, it's 1 over t.
Yes.
And then if it can be 0, then there is something related to pi squared.
Pi squared diameter. Pi squared times the diameter.
Yeah. So is there a formula that is valid in both cases? Like.
I guess there is. Yeah, actually there is. There is something which interprets between diameter and, but that's, sorry to say, I would prefer this thing. So that formula, diameter is really in higher dimension, it's really very bad parameter. It tells you almost nothing about the behavior. I would really like to introduce, and on the other hand, the covariance matrix, the operator norm is really substantial. So I would be happy to see Riemann analog of this thing. Okay, so, and in your question, so there is let me just, why do I know automatically that it's known? Because there is a technique called Dirichlet decompositions that reduce matters to one-dimensional objects. So basically you need to check, you have an interval of some length and you have some Gaussian of that thing, you need to check the progression, you get some estimate, that's how you can interpolate between the Payne-Weinberger and the Lichner-Horowitz thing. This I'm sure that it's like an exercise if it's not written.
Okay, that's the end of it.
That's a good sign.
The end of it. Thank you. So thank you, Boaz, for these 3 talks on the unreasonable effectiveness of convexity.